that's funny. All right, let's try this again. All right, let's start recording. All right, let me just quickly repeat what I said, is that we will continue with new work in the lectures. We'll do revision in the tutorials. We've covered all of the work for the semester test a while ago. Even the exception handling we're doing today and the DLLs we did last week is technically bonus. And we will be creating, I will do some revision as well as when we cover the new things, because there's always some stuff that can be mixed in. All right, so that's good. Let's stick to that. All right, so exception handling, problems that exist with normal number-based error handling. Oops, with normal error codes, is that you need to know what those codes mean. Obviously, you can document your codes well, and you can use meaningful error names. But again, also the issue is you don't give much control over to the person who's using your data structures or using your libraries what to do with those errors. At the moment, we just exit with an error code, which stops the program. What if the person had a plan how to deal with that error? What if it wasn't such a severe error? We've taken control away from the client programmers, the people using our data structures, away from them. Wouldn't it be better to tell them this kind of error occurred? What do you want to do about it? So exception handling gives us the ability to do that. It lets us more meaningfully describe the kinds of errors that occur, because we can mix it with inheritance to say that different kinds of errors are related to each other in certain ways. And we can include information in the error itself that may be useful to the person who wants to do something about the error. And also, it basically is a mechanism for us to give control back to the person who's using our data structure, so that they don't have to rely on us making a decision for them about ending the program or whatever. We let them choose how to handle the error. They could end the program or just report the error or maybe correct the error. It now puts control back in the hand of the client programmer. So those are the advantages of exception handling. So we'll learn what an exception is. We'll learn how to handle exceptions within a program. We'll use a try-catch block to handle those exceptions. C++, obviously, the standard library comes with a built-in exception class, which many people will derive from to create their own special exceptions. We'll create our own exception hierarchies from scratch, but you'll often see people extending the existing exception classes in C++. And then we'll talk about when you find the error, what do you do with it? You basically give control away from where the error is found, and then the error exception handling mechanism must find someone to deal with the error. So that act is called throwing. You can, of course, do it multiple times, which is called rethrowing the exception. And we'll see how this mechanism actually works in terms of how the function call stack, so basically the information stored in memory that's got the return address of the function as well as the local variables and all of that, how that gets handled when you use exception handling. Because the question would rise up, if it's so great, why don't we use it everywhere? And also, what would be so wrong about using it for something other than reporting errors? And both of those are consequences of looking at the cost of exception handling in terms of unwinding the stack, basically undoing the function calls so that you can find the block of code that's been designated as the error handler for this kind of exception. So an exception is a non-standard state in your program, and it's particularly one that's got some undesirable consequence to it. So it could be you expected the string to store a numerical sequence of symbols, but instead it stores something non-numerical. This is a state that is not allowed by the logical properties of your data type. So we need to signal that that this undesirable state has been reached. So the exception is the event or countering this undesirable state that you've detected. Then we basically split the act of finding the error and the act of dealing with the error into two separate blocks of code. Sometimes they occur right next to each other, but they don't have to. They can be separated arbitrarily far apart from each other. In fact, it's very common to see the error handling code be in something like main, whereas the error detection and signaling code be stored in the data structures themselves. So exactly what you do with different kinds of errors depends on the kind of application you're being developed. For example, detecting an invalid numerical sequence string would be a small problem if this was data that the user was typing in. You just ask them to try again, but a big problem if you're processing some historical data file which is supposed to be correct. So the level of response finding that error differs depending on the kind of application that's being developed. So if it's a file that's being processed, you may very well want to terminate with an error, because continuing on with this clearly corrupt file could be worse than stopping and letting people know that the file is corrupted, or the format has changed, or some other reason the wrong kind of data is in the wrong place in this file. Whereas again, in a user interface, it's not a big problem. The user is there, it's real time. You just ask the user to try again, so not a big deal. So what we do is we'll add exception handling code, or rather, exception handling is two phases. There's the raising of the exception, which is finding the problem and signaling that it's occurred, and then there's the actual dealing with the problem. So we will detect and raise the exception at the point in the code where the error can occur, and we will handle it in terms of actually dealing with it in a separate place. You've seen exceptions in a sense if you've used the assert functionality in C++. Technically what it does is it raises an exception if the condition isn't true. So you've indirectly used exceptions even if you haven't directly used them. But again, assert is a very blunt force error handling mechanism and is intended to handle programmer errors, not user errors, because the idea is that you turn assert off once you're reasonably sure that your code is correct. Obviously, the user can type in nonsense, or external files can be corrupt and so on. You can't ensure that's not going to be the case, but you won't use assertions to deal with that. But it's your fault if you pass a null pointer to something that doesn't expect a null pointer, or if you use a negative size for something that's supposed to have at least 0 or 1 as their size, and so on. So an example of something is a division by 0. Many runtime environments will trigger a division by 0 error, which may well be handled by the runtime environment itself with no effort on your part. C++ tends not to do that, but you'll see in other programming languages it's very common for those kinds of mathematical errors to be dealt with internally by the language and for it to raise an exception when that occurs. With C++, it depends on the data types involved, but for example, if you divide a double by 0, you're going to get one of the non-numerical values stored in the double, such as not a number. Nan, but the point is still the same. You'd use an assert if you were taking control over to test that the divisor wasn't 0 beforehand. I've noticed a prompt that someone has typed something, so let's just see what questions are there. Yes, absolutely. That is exactly 100%. So assertions are for program errors, not for user errors. Assertions are expensive. And they also embed bits of your code in your executable, because I'm sure you've noticed when you run an assertion and the assertion fails, it spits out the line of your code which triggered that error. So that could be a problem if you've got sensitive company secrets in that line of code, or even if you've just a programmer who tends to use rude words in naming their variable names. That could be an embarrassment if that was spat out to the user of your product, for example. So you typically will turn assertions off in the final build of a program, because the idea have found those problems already. So yes, it's a good key point to note. Exception handling is more general, though. Exception handling gives you complete control over what kinds of errors exist and the separation between finding errors and dealing with errors, which is why it's so widely used. All right, so exception handling is expensive, though, because it basically needs to do a lot of extra bookkeeping in code that might cause a problem, because it needs to be able to undo the function calls and basically what they call unwind the stack. So every time you call a function, the return address of the function and the parameters and local variables are all stored in a data structure called the stack, which we will start the stack immediately after this. We'll build our own stacks even, but within the computer, it refers to the portion of memory that's automatically managed in a very rigid way in terms of the data in and data out. We'll explore those rules in the next section. But the point is that to be able to undo that nicely and find the place where the error is supposed to be handled, extra bookkeeping information needs to be added to each of these they're called stack activation frames to basically allow the function calls to be undone. And the act of undoing them is also time intensive. So you don't have exception handling on everywhere in C++. Some programming languages do, but C++ and many languages, to be honest, say that you must specify which region of code is vulnerable to errors. And the exception handling mechanism will be on for that region of code. So we call that, we signify that region of potentially error-prone code using a try block. And then we will specify how we handle those errors using catch blocks. So the error handlers for each kind of error will be specified in catch blocks. The place where the error is found will make use of a throw keyword to signal the kind of error that was occurred. So the exceptions are detected with normal if statements or whatever, then thrown within a try block or some scope contained within that try block. You don't literally have to see the keyword try there, but any function that's called from a try block will still be in that try block, and any functions they call, which they call, and so on and so forth, will all still be quote unquote inside the try block, because all the stack activation frames that are created from that point onwards will have the necessary bookkeeping information for undoing the stack. You must be thrown within a try block or some nested scope within the try blocks, and then caught by a corresponding catch block. And C++ does come with some built-in exception handling classes. And the best way to use exception handling is to create a family of related classes, so base classes and derived classes, that reflect how the errors are related to each other. So you could have a base class that represents just exceptions, and then let's say you're dealing with number-related exceptions. You could have a numeric exception that derives from exception, and then let's say you've got division by zero as a kind of numeric exception, so it could extend numeric exception, and range errors on numeric exception, so they could extend it, and you could have min range errors and max range errors that extend the normal range error, and it's at each point you could add more information that might be useful to the person who's dealing with the error. So the best way to handle exceptions is with a hierarchy of classes. So we often mix inheritance in with exception handling. You'll see some of the older papers actually tested the two together as a compulsory section, where we would test the inheritance along with the exception handling. And the reason is because they go together so strongly. C++ is unusual, though, very unusual, in that it allows you to use any data type as an exception. So it doesn't have to a class created for that purpose. You can throw the value true, or you can throw the value false, or you could throw a string, or you could throw any number of things, which is weird. So you'll see that we always account for this possibility that some code that our code calls might throw something weird. And we handle that by including a special uber general catch block at the very end that will handle anything that we forgot to handle. So statements that may generate an exception, so potentially error-prone code, is placed in a try block. The try block will also contain statements that should not be executed if an exception occurs. So that's very important, is that when the exception occurs, the flow of control stops. We'll show that to you in an example. And so what's nice about that is you can write the rest of your code in the try block as if the error never occurred, because if the error occurs, that code won't be executed. So you won't have wrong values propagating through your code. You know for a fact that the flow of control will stop, and the value that could potentially be incorrect will not be used, and some other error handling code will deal with it. So that's very powerful. And then the try block is followed by one or more catch blocks. And we'll see that the order of those catch blocks is actually important. You must catch them in the order of most specific first to most general last, because it will stop when it finds a catch block that can do the job, not necessarily the best catch block for doing the job. So this is the syntax. Try, your potentially error handling code, and any functions they call will be protected. And then catch blocks for each of the kinds of errors that you occur. So typically you'll have an exception type and an identifier for that exception, so that you can get any details that are stored within the exception class, maybe a message. If it's a min or a max range exception, maybe you store the values that violated the range or something like that. And just, it's not actually shown in this example, but it's super common to catch these by reference, because what you often do is you might mix polymorphism in so that you can have polymorphic error handling, so that you don't have to catch every possible version of a numeric exception. You can just catch the base numeric exception type and know that polymorphism will sort things out to some degree. So it's very common to catch these by reference, so just data type 1 reference identifier. And then at the very end, this is ... these ellipses dots. It's not a notation to say that, whatever. It literally means handle any error. You won't get a variable because it could be literally anything, but anything that doesn't get caught in the previous blocks will be dealt with there. So you'd have some very general, some unknown error type occurred, message displayed here. These dots, however, that just means you can have any number of them. So don't literally type these dots in, but do literally type those dots in as your final catch block. So the catch block specifies the kind of exception it can catch, and then the curly braces after it contain the code you want to run when that kind of exception occurs. So you could just report the error, you could try and correct the error if it's correctable. So for example, you might handle a range exception by capping the value at some maximum or minimum, or you might handle division by 0 by instead dividing by a very small but non-zero number, like 0.00000000001, which will then give you a very large result, but not an error. You'll see a lot of mathematical formulas where there's a potential division by 0 will have a small epsilon value defined if 0 is epsilon, if the divisor is epsilon. So you could handle it that way, or whatever. It all depends. The point is that you actually give control over to the client program about how they deal with it. You don't make those decisions for them inside the data structure. If no exception is thrown, then nothing happens. So the catch blocks only run if a problem occurs. They're emergency protocols, basically. What you really want to happen is all the code in the try block runs successfully and nothing bad happens, and then code resumes after the end of the last catch block. So that's the ideal normal path through your program. And once a catch block has been executed, the remaining catch blocks are ignored. So that's why it's super important to put them in the right order. If I put this general catch block up at the top, it would always catch the exception, and none of the remaining ones would deal with it. So if we're looking at the example I spoke of, you'd catch like a min range exception first, then a max range exception, or the other way around. They're at the same level. Then you'd catch other kinds of range exception. Then you'd catch numeric exceptions. Then you would catch exceptions. Then catch anything else. So you always do it most specific first, most general last. And yeah, so the catch block parameter becomes a placeholder for the value thrown. So basically, if I threw an exception class E and put values inside it, those values would be accessible from that identifier in the catch block. Okay. And so the act of detecting the error, that's done normally with an if statement, but the act of actually signaling or raising the exception is done using the throw keyword. So you'll say throw and then some value, which will typically be an instance, an anonymous instance, since there's no point in giving it a name, of your class. So basically, you'll just call one of the constructors for your class then and there, and that'll be that. So it can be any value, but typically it's an object. And it's typically an anonymous object, to be perfectly honest. All right, so an exception is a value, and it's got nothing to do with the name you give it, which is why you can give it no name at all, to be perfectly honest. So yeah, so catch blocks, as you see, in the order of the catch blocks is important. Exceptions catch a specific type or all types of exceptions. So dot catches any kind of exception, but doesn't give you a variable to work with because it could be anything. So if you do use it, which we will, it should be the last catch block of the sequence. So be careful about the order. Most specific first, most general last. This is the most possible general one, so you should include that as your absolute last one. All right, so typically with exception handling, we'll do it with classes because we want the way the classes relate to each other to be the same as the way the error types relate to each other. So we'll use a hierarchy of derived classes to represent that. C++ has a built-in exception type called just exception, lowercase. And it's the data it stores is basically just a string describing what the error is, so whatever message you want to put in it, which is returned by the horribly named what function, so just for what it's worth. But you could, of course, extend it and add more meaningful data members to it and accesses for them if you wanted to as well. We'll typically create our own exception hierarchy, though, altogether. So, for example, if you want to dig into the exception classes that come predefined, they've got logic errors that are predefined, invalid arguments that are predefined, out of range errors that are predefined, length errors, runtime errors. For example, when numerical values go above their maximum, so overflow errors, or technically, let's just be clear here, underflow is not the same thing as negative overflow. So let's say if we've got a 4-bit number, 1111 is the maximum value that can be stored. If we store one more in it, it overflows to 00000. Let's say it's a binary number. That's an overflow. Some people think that the reverse, like for example, if I tried to, let's say the maximum real number I could store was 1337.0. It's obviously not, but just imagine it was. And or rather, if the negative one was minus that. If I try to go smaller than that, I wrap around to the maximum value. That's not underflow. That's still overflow, but just overflow in the opposite direction. Underflow is where you try and store a number that's too small to represent. So if I try to store the number 0.0000001, it's too small for C++ to represent and vanishes. That's an underflow error. Your number became too small to represent, not an overflow error. It's just bear that in mind. We're not going to really be making use of the built-in classes, but they do exist for you. We will create our own exception classes to handle errors related to whatever it is we're doing. C++ doesn't care. Like honestly, if you throw a Boolean or you throw a C++ built-in class or you throw your own class, it's the same mechanism. I don't think it's good practice to throw raw values, like just to throw true or whatever. It's very useless for the person to deal with. I mean, maybe in a very limited context it could make sense, but I always will use exception classes that I define to be my exception types. But it can be any class, to be perfectly honest. But I will always make it an exception class specifically. It's how you use the class that determines whether it's an exception class. So if you use it in a throw, it becomes an exception class by default. There's no magic to it, but we will stick to custom ones. Typically, there won't be that much going on inside the exception class. Its job is just to signal the kind of error through type, and then any extra information you may need, which at bare minimum, well, is nothing because the type itself can signal what kind of error occurred, but maybe a string message, or if there are numerical values associated with it, like range errors, you could include those as well. So the C++ by default just has the string what to represent the message you declare. So exceptions can be handled in a catch block, or maybe you realize that this exception is too difficult to handle here, and you can rethrow it for some other containing scope to handle. So the basic idea is an exception gets detected with an if statement somewhere deep inside your data structure. You throw it there, and then the code that used your data structure catches it, maybe deals with it, or maybe doesn't. And if it doesn't deal with it, it can throw it again for some other catch structure to handle. So think of it like this. Imagine you're traveling and you're catching a plane or a bus or something, and you see this suitcase, and this suitcase is ticking. So obviously you conclude this is definitely a bomb. So you pick up the suitcase, and now you have a choice. Do you know how to defuse a bomb, yes or no? The answer is probably no. So what do? You throw that thing, you yeet it as far as you can away from you. And then hopefully someone catches it. So let's say someone does catch it, and that person happens to be a bomb disposal expert. Awesome, they defuse the bomb, no problem. If they too do not know how to deal with the bomb, they throw it again. And if it eventually makes it to the end of the platform and no one has dealt with it, then everyone is having a bad day and no one gets to travel. So it's the same thing that happens in your exception handling code. you can catch an exception, and if you can't deal with it, you can rethrow it, which just means that the exception handling mechanism will kick in again and look in your containing scope to see if there is some catch block that will deal with the error again, or an error that's related to it. And if it makes it all the way up to main, so basically if the exception bubbles all the way from where it was found up to main and no one has caught it, then your program will crash. And that's what should happen. So it'll be an unhandled exception, we call it, and that will terminate the program. So an exception occurs, you immediately pass control to one of the catch blocks, which either deals with the exception. It can partially process the exception. So what you could do is you could have the first level just catches the exception and maybe logs that the exception occurred, then rethrows it to see if someone else can actually deal with the problem. That's a very common approach. And then, or it can rethrow a different exception as well. It doesn't have to rethrow the same value. You can throw a different kind of exception that maybe signals that the thing has been logged. So you catch the normal exception and you throw a logged exception or whatever. That's entirely up to you. And then what is actually reasonably common is you'll see most of the exception handling code will be in one place, and that place in your such circumstances will typically be in main. So the syntax for rethrowing an exception is the same. It's just to throw again. If you don't specify a new value, it'll just rethrow the same exception you caught, or you can throw something else. Or you could throw the variable that contains that exception as well. That'll work just fine. Some languages have a different keyword for throwing an exception a second time. If I remember correctly, Object Pascal, for example, Delphi had a re-raise keyword, if I remember correctly, for rethrowing an exception. C++ doesn't. It's just the same. It doesn't really care. And then yeah, you can throw a different value if you really want to. Again, the object being thrown can be a specific object, an anonymous object, which is typically what you'll do. And you can, if you want to, and this is totally optional, you can specify the kinds of exceptions that can be thrown in a particular function. So the keyword throw can be used here to indicate a list of the things that the exception can throw, or the kinds of exceptions you expect might be generated by this function. In a sense, this is really just a kind of documentation. The IDEs might use it, and you may get some warnings related to that. But it's very common to not specify that, and for people just to use the catch-all block to deal with anything that they didn't expect. But it is worth noting that you can explicitly mention the kinds of exceptions that can be thrown. It's good practice. To be honest, we don't really do it. We probably should, but it's not required by the language. Some languages, as far as I remember, Java, which we'll do next year, does require you to explicitly account for every kind of exception that could possibly occur, which means you'll see a lot of boilerplate exception handling code that does pretty much nothing except quite the compiler down, which is not the point of exception handling. If exception handling is there, it must do something, even if it just logs the exception. What people do in languages like Java, which is a bad practice, is just to make the compiler happy. They will catch an exception, and then there will be an empty exception block. It won't even output that the exception occurred. It's called squashing the exception. So people will run the code, no exceptions, but something's not working, and it's very difficult to debug systems like that. So if you are going to list the exceptions, make sure that they actually can get raised, or don't list them as well. Okay. Once an exception occurs, what do we do? You've basically got three choices. You can terminate the program. You can try and recover from the exception. So as I said, for a range exception, you could cap the value maybe, or if there's a reasonable default value, you could use it instead. You can substitute that, log the error. You could log and do the rest as well. No problem there. The question is, when should you terminate the program? So typically, if continuing with wrong information is very dangerous and it's a mission critical system, and there's no way for a user to automatically correct the problem, or immediately correct the problem, then terminating the program is a reasonable thing to do. People say, oh no, the program crashed. It's better if the program crashed than the program continued correctly. That's a much worse outcome. So for example, if a file is corrupted and it's supposed to process the file in some way, and it's not an interactive program that the user is working with directly, but something that's been called by a script, having it crash and do nothing is much better than having it spit out an output file that's wrong. So that's how your compiler behaves. If you've got errors in your code, does it spit out a wrong program? No. Well, I mean, if you've got syntax errors, it doesn't just guess and then say, well, it's close enough, I'll just continue ignoring your wrong stuff and spit out a program that does everything except the wrong stuff silently. That would be terrible. It refuses to compile and stops. So terminating is a valid option sometimes, and usually there'll be an appropriate error message that goes with it. Other times you will want to fix the error if you can. So you will need to deal with that in different ways, reprompt the user if it's interactive, substitute a reasonable default, cap, whatever. I can't list all the possibilities there. It all depends on what you're doing. But if there is a way to fix it, you can continue. And then logging the error and continue. So it might not be possible for a program to stop. So the program might need to continue because it's doing some mission critical job, but it won't continue with that particular data item and needs to move on to the next one or keep doing its other important functions. So in those cases, it'll log the error and maybe log it quite notably. Maybe an alarm even goes off or emails get sent or whatever. But the program has to continue. So if it's doing some mission critical job, running a nuclear reactor or monitoring a satellite, or even just keeping your business payments going, you know, if one credit card is number is malformed, it shouldn't bring down the whole credit card processing system. It should carry on with all the ones it can carry on with, but it should definitely log the one that didn't work. And that's basically what you do. Is you log it somehow, write it to a file, for example, and just continue. So now we see what is the mechanism that occurs when an exception handles. I just want to check if there are any more questions before I do that last bit. Okay. That if we did not have try catch, we would simply use the function that returned the class reference. Yes, that is another way. So people do that, use return values, for example, instead of exiting with an error code or whatever. And it works, but everyone has to check for the error code. So there's so many, I can promise you, there is a lot of code that returns success values or you know, extra information about whether or not it worked, that people just throw away the return value and don't even look at it. Exception handling, you can't just ignore the return value. Your program will crash if you don't deal with it. So there is that is a valid approach, and people do it, but it does require good behavior on the part of the person using your code to actually deal with the return values that signify success or failure. All right. All right, what is the difference between in terms of if I throw a number? Oh yeah, okay, so that's fine. So if you throw the number, then somewhere there will be a catch that will catch, let's say catch int, and then code that deals with it. If you exit, the program will stop immediately right then and there, just dead in its tracks. So any cleanup code you might have expected. So for example, particularly if you're dealing with files that need to have like a post-amble written to them for them to be correctly formatted, that would be very bad because your file would only be half written and it would be corrupted. Let's say, for example, you were doing a file of all the students who had done something, and there was a student whose student number was corrupted. But rather than just terminating immediately and having a corrupted output file, you could skip that student, output an error message, and then make sure you continue to the end and output end sequence in the file that makes it valid. So the exception handling is more gives more control to the user of your data structure about what to do. Oh, that's a good question. So when testing, you just deliberately put in error message, invalid values. So let's say, for example, the inputs are coming in from the command line. You can just manually put in negative lengths or impossible coordinates or whatever, and make sure your code corrects it, handles it. So this is, okay, and I will repeat the disadvantages now. So this is actually a really good question. So an important shift in the way we program that's happened in the last, let's say 10 years or so, but maybe more in the last half of those 10 years, has been a shift towards what they call test-driven development. So the idea is that testing a program is a lot of work, and it's something that you shouldn't just throw away when you're done. You should keep your tests. So typically, your tests are in a sense programs that run your code with different parameters, correct ones, incorrect ones, values that are just in range. But border cases are super important, like things that are exactly length rather than any edge case you've got is something you should test. So what you should do when you're writing a complex system is you should actually automate your testing process, and you write programs that automatically test your code. And then when you make it, and if you keep doing this consistently, it's really useful and powerful, because then later on, years down the line, when you have to update a program, and updating something that already exists can introduce all kinds of bugs. But if all of your testing is done by a program, you can rerun those old tests to make sure you haven't introduced any weird errors that you might not have expected. So test-driven development, this whole software frameworks for automating that these days. But it's a great question. So you have to test it. You have to make sure that you trigger the errors. And then the disadvantages of exception handling, it's slow, right? It's definitely much slower than unexception handled code, because it has to do extra record keeping to be able to find the catch block for a particular throw. So it is much slower. So that's probably the main advantage or disadvantage. And C++ being performance oriented doesn't. I don't want to try crashing my code during the test. Crashing is fine. Crashing doesn't cap your mark. I'd rather see a program crash than a program not compile. So I mean, you can get really good marks. Like, let's say your program's crashing because you've got a -1 somewhere instead of a +1. And fixing that one small thing would make your code work perfectly. You're not going to be capped because of problems with your input. Crashing is not something to avoid. Crashing is good because it points out where the error is. The worst thing is to think code is correct when it's not. So because the BCS requires it, so why is there a cap on compilation? The BCS asked for it, most importantly. And secondly, if you're not even producing a valid C++ program, what is the point? Your job is to write correct programs, but one that doesn't compile isn't even a program. There's an infinite set of strings out there, and only a subset of those strings are valid C++ programs. If you've given us one of that infinite set of invalid strings that are almost C++ programs, then what have you produced? Thank you. Excellent. The attendance code is I don't know, was here. There you go. Okay, and then there was a question here. So what are the common errors that would require exception handling? Range stuff, the stuff that the C++ class is built in a lot, logical errors, range errors, opening and closing of files, and any resource that needs to be acquired, used, released, and can be locked if it's being in use by someone else. Those almost always require exception handling. So things like files, things like database connections, things like network sockets, lots of things like that. So yeah, what will cause a program not to compile? A syntax error, and only syntax errors. Logical errors or semantic errors obviously cost you some marks because your correctness is off, but they won't cap you. Only syntax errors will cap you. Yes, a missing semicolon will make your program to be capped. Don't do that. Be good, right? Get good. Like you're in the second semester of your first year. You've almost got a year of programming underneath you. You should be able to identify when you've got a missing semicolon and fix that for sure. All right. Okay, well, we're about out of time, so I'll go through the stack unwinding and do the example tomorrow. But yeah, the stack unwinding is so short. Let me just quickly do that. So, and I've actually mentioned it normally anyway. So what happens when the exception is thrown is that the program, I know we've done that already. Yeah, so when the exception is found, the stack is unwound. So basically it reverses the function calls to try and find an enclosed catch block. So I don't think there's actually anything more that I haven't said already. When the stack is unwound, if it reaches main, it terminates. Memory for its local variables is destroyed. Yes, that's important. Those local variables don't exist as the stack unwinds now. And it continues until either it finds an appropriate catch block or hits main. And if it hits main, then the program is terminated. So that's it. All right, so we've covered the theory. We'll do an example tomorrow. I hope you all have a good Yeah, we're doing revision in the tutorials. And then please also, there is a good revision mock test that's on Eve now. It's from a couple of years ago, but it goes through the whole process in a very detailed way. Okay, yeah, we'll put the link up for the online writing semester test 2 today. So thank you for reminding me. Prac 8 is also revision. That's fully correct. It's a past paper, and we'll do other past papers in the tutorials. Yeah, I know. That music was very soothing, maybe too soothing. I don't use that track anymore. But thanks. I did post the attendance code. This is it. Was here. Okay. All right. Thanks a lot, guys. I hope you have a good afternoon. Yeah, don't worry. As I said, I don't use that code, that music anymore. All right. Have a good afternoon. See you guys tomorrow. Bye.